Everyone had a happy, let's see, make sure you've got that you're recording now? Okay. All right, so yes, I hope you had an enjoyable extended holiday break. I hope it was safe for you, and hopefully you're all ready to hit the ground running and learn about benzene and aromaticity. Okay, so if you were in the class last semester, you remember we had the Bacon quizzes. They were online tutorials that had quizzes attached to them on certain topics. They're optional. There is a small fee, about $6, I believe, to register for those. And if you choose to participate in the Bacon quizzes during the semester, the average of your Bacon quizzes can replace your lowest in-class quiz score. So it gives you another opportunity to replace a lower quiz score. And there's a handout on the Bacon quizzes on Learning Suite, so you should download that and take a look at it if you're interested. We'll have more Bacon quizzes this semester than we did last semester. There's more topics this semester that intersect with those on the Bacon system. And the first one is Diels-Alder chemistry. So there is a quiz, a Bacon quiz on Diels-Alder reactions that is currently available. And remember, you can do those Bacon quizzes anytime from now until the end of the semester. Some students use them as a way to study for the exams. Exam number 1 is going to be at the end of the month, so you could do this Bacon quiz at that time. Other students wait until the end of the semester and use them as a way of reviewing for the final exam. Okay, so that's available. Today, we're going to talk about aromatic compounds. Benzene, which we introduced at the end of our last recorded lecture, is the prototypical example of an aromatic compound. We'll start off talking about nomenclature of aromatic compounds. We'll talk about interesting aromatic compounds. And then at the end of the class, we'll discuss the concept of aromaticity, which is this, it's not related to the odor of the compounds, it's related to the special stability that these compounds exhibit. Okay? So here on the screen, we have the figure that we ended with in our last recorded lecture. We have an electrostatic potential map of benzene on the right, showing the electron-rich region due to the 6 circulating pi electrons above and below the plane of the molecule. And then here we see an orbital picture. This is all smeared because the 6 p orbitals are all conjugated. They're all overlapping. Each p orbital is overlapping with 2 adjacent p orbitals. And so we see that we have just a smear of blue on the top, a smear of red on the bottom, due to that full and complete conjugation. So the term aromatic refers to the fact that some of the first benzene derivatives isolated from nature were isolated from these fragrant trees. And so they were good smelling compounds. And so compounds that were similar to benzene in structure were called aromatic compounds at the time. Many of them stink, in my opinion, so I think it's a poorly named. I don't think it was the benzene derivatives themselves that smelled good. I think it was other things in the extracts from these trees that actually smelled good. So today, the term aromatic or aromaticity has nothing to do with the odor of the compound and everything to do with the fact that it has special stability similar to that of benzene. As we discussed in our last lecture, benzene, even though it has 4 degrees of unsaturation, does not undergo addition reactions. Okay, so its unsaturated system is incredibly stable. So whenever we encounter a new class of compounds, the first thing we have to do is nomenclature. And of course, we're going to spend as little time as possible on nomenclature, but there are some things that we need to learn in terms of being able to name benzene derivatives or substituted benzenes. The first thing is that there are some common names involved with some of our more common substituents. So methylbenzene is actually called toluene. Nobody ever calls it methylbenzene. Everybody calls it toluene. So we have to memorize that common name. This hydroxy substituted benzene is known as phenol. And these are acceptable names in IUPAC nomenclature. And then an aminobenzene is known as aniline. Okay, so we have to know these common names. If we have substituents that are not one of these three, then we just use our normal IUPAC naming system for naming those substituted benzenes. Okay? So what would this molecule be called? Anyone? Yes, please. Isopropyl benzene, okay? I know why you said toluene, because it has an alkyl group on it. But if that alkyl group is not a methyl group, then it would be benzene. It's only toluene if the alkyl group is a methyl group, okay? So this would be isopropyl benzene. Okay? Our next substituent that I'll show you is one that we haven't seen much. It's not as common being attached to alkanes or alkyl groups, but it's very common being attached to benzene rings. NO2 is referred to as the nitro group. So knowing that this is the nitro group, what would we call this compound? Nitrobenzene, yes. Okay. And why are we not using numbers in these names? There's only one group. How many molecules could you draw that would fit the name isopropyl benzene? There's only one. So if there's only one that you can draw, there's no need to use a number. Okay? But of course, carbon 1 is the carbon that bears the substituent. We just don't need it in the name. Okay, if we have two substituents, there are three possible patterns. We can have those substituents adjacent to each other. So now we would need to use numbers, and 1 and 2 would be the numbers we would use if the substituents were on adjacent carbons. But we have special names for these patterns with benzene. These only work with benzene. They don't work with other rings. When we have a 1,2 substitution pattern, that's called ortho. And it's often abbreviated with an O. That O is usually drawn in italics, but I can't draw italics very well on a chalkboard. If you have one carbon in between your two substituents, that's a 1,3 substitution pattern. That's referred to as meta, or M. And if we have a 1,4 substitution pattern, if our two substituents are on opposite carbons, opposite sides of the ring, that is referred to as para. Sorry. Okay. And as I mentioned, these letters are usually italicized. So we typically just use the letter when we're writing the name, but when we're saying the name, we would say ortho, meta, or para. Okay? All right, so let's do a couple of examples to make sure we can apply the ortho, meta, and para nomenclature. And there's a couple of different ways that we can do this. Okay? All right, so here we have two of the same substituent. Who would like to raise their hand and take a stab at coming up with a name for that compound? Go ahead. Okay, ortho dibromobenzene. So we use the di prefix because we have the same, two of the same substituents. Okay, ortho dibromobenzene. Okay, very good. If we have two different substituents, now we will alphabetize them. Okay. Who would like to take a stab at naming this one? Okay, go ahead. Okay, so you don't need the numbers in this case. The M or the meta will suffice. But which substituent did you name first? Fluoro. Okay, so we go alphabetical. If you wanted to know which carbon was carbon 1 and which one was 3, it would be based on the alphabet. So this would be carbon 1 and that would be carbon 3. But if we don't need the numbers in this case, we just use the meta prefix to indicate the 1,3 substitution pattern. Okay? And if one of our two substituents is one of our 3 common substituents that has a common name, then we use the common name as the parent. Okay? So I'll show you how that's done. So what is our common parent name in this case? That's toluene. Okay. What do you think is going to go in front of the toluene in this case? Okay. We're going to put a para, and then what goes next? Bromo. Para-bromo-toluene. Okay. So the toluene name has the methyl group already embedded within it, so we don't need to name methyl as a substituent. We would just say para-bromo-toluene, and that tells us it's this molecule right here. Okay? Any questions on the use of ortho, meta, and para? Okay. So we can have more than 2 substituents on a benzene ring. We can have 3 or more substituents. And when we have 3 or more substituents, we're going to use numbers in these cases. And we're going to, the guidelines we're going to follow is we're going to assign the lowest set of numbers that we possibly can assign. And we're going to alphabetize the substituents at the front of the name. And we're going to use our common roots, our toluene, phenol, and aniline, anytime we have one of those common substituents. And if we do that, then this substituent is automatically going to be at carbon 1. Okay? So let's look at some examples. And all right, so what's our parent name in this case? Okay, so this is aniline. Okay, what's the first part of our name in terms of the prefix? First part of the prefix. Remember, we alphabetize when we have multiple substituents. So what's going to go first? Okay, ethyl will go first. And what number is going to go in front of ethyl? Okay, we'll have a 3 because the amino group is at carbon 1. So it's 3-ethyl. And then what's the missing part of our name? 2-propyl. Okay, 3-ethyl, 2-propyl aniline. Okay, any questions on how we came up with that? Okay, let's do one that doesn't have a common substituent or a common name associated with its substituent. Okay. So in this case, benzene is going to be our parent name. And we're going to give the set of numbers that gives us the lowest set, okay? We can use the first point of difference rule to figure that out. And then we alphabetize the substituents at the beginning. So what's going to come first in our prefix of this compound? Okay, so we'll have ethyl. What's the number of the ethyl substituents? Okay, it would be 4. Good. And then what's going to come next? Okay, 1-fluoro. And then what's the missing part of our name? 2-nitro. Okay. 4-ethyl, 1-fluoro, 2-nitrobenzene. All right, so we can pick any of our carbons with a substituent as as carbon 1, but then we're going to want a number in a way that gives the lowest number to the next substituent. So you could either go 1, 2, or 1, 2. And so then you would want to, of those two choices, you'd want to choose the method that gave the lowest number to the third substituent, which would be 1, 2, 3, 4. Okay? Any questions on how we come up with a 1 for the fluoro, 2 for the nitro, and 4 for the ethyl? Okay, good. So we can also have benzene or benzene derivatives as substituents if they are attached to a longer chain, a chain of 7 carbons or more. You would name the chain as the parent, and you would name the benzene ring as a substituent. So in that case, so this squiggly line is telling us where the benzene ring is attached to our longer chain, and this is known as a phenyl group. So benzene as a substituent is called phenyl. So phenyl means C6H5. It's abbreviated as pH. This is not phosphorus. This is not referring to the pH of a solution. Capital P, lowercase h is referring to a phenyl group. In fact, we use this abbreviation many times as shorthand. So if we want to write benzene, but we're too lazy to write benzene, or we're too lazy to write C6H6, we'll just write PHH, and that means benzene. Okay? We could do the same thing for toluene. PHCH3 would be toluene. PHOH would be phenol. So you'll see this pH abbreviation quite frequently, and it refers to phenyl. We could have a substituted benzene or a benzene derivative as a substituent of a longer chain. And I'm just going to draw a line to the center of the ring, indicating that we have an R group, and that R group could be on any of the carbons of this ring. It doesn't matter where. That's what this line to the center means. And this is referred to as an aryl group, A-R-Y-L. Okay? Aryl group is a general term in the same way that alkyl group is a general term. We know what alkyl group refers to. We used that term frequently last semester. Aryl group just refers to any kind of a substituted benzene as a substituent. Okay? And that is just referred to as an aryl group. And then if we have benzene and we have an sp3 carbon, and then that sp3 carbon is attached to a longer chain or to some other sort of a group, this is referred to as a benzyl group. Okay? So a benzyl group, that is C6H5CH2, and then that's attached to something else. That's often abbreviated as BN. Okay? So if we have this molecule, most organic chemists would refer to this as benzyl bromide. So that's an example of how you would use the term benzyl in a name. This is a common name, but it's a well-accepted common name. And the BN abbreviation is also well accepted. So if you wanted to write the formula in shorthand instead of writing C6H5CH2Br, you could just write BNBr, and that would refer to this compound. Okay? So it's important to not confuse the phenyl group and the benzyl group. Phenyl is just the benzene ring directly attached to a longer chain or to another species, whereas benzyl refers to a benzene ring and an sp2 carbon, a CH2, and then is attached. Okay? Any other questions about nomenclature of substituted benzenes? Yes, please. But between that one and what was the second part of the question? So you're saying, what if we called it meta-nitrofluorobenzene? You mean, well, anytime you have a 1,3 relationship, it's always going to be metafluoronitrobenzene because you could always just rotate it and it would look the same as this. If you had a different pattern, if you had the substituents next to each other, then it would be ortho. If you had the substituents opposite each other, it would be para. But if you put these two substituents on these two carbons and they had a 1,3 relationship, it would still be the same. It would still be metafluoronitrobenzene because by rotating or twisting, you would get the same compound. Does that answer? Okay, so the mirror image of this is this molecule. Would the mirror image of this be superimposable? It would. It's a planar molecule. So anytime you have a planar molecule, the mirror image of a planar molecule is superimposable. And so the mirror image is identical. Okay, so in this case, the mirror image would be the same. Okay, other questions? Let's talk briefly about the spectroscopy of benzene and aromatic compounds. So in the IR, the most important absorption is the sp2 carbon-hydrogen stretch. That's going to show up just above 3,000. Of course, that's not going to be distinguishable from alkenes. If you have a peak in that region, it would tell you that you had either an alkene or you had a benzene, or you might have both. It doesn't allow you to distinguish between the two. You're really not going to want to look at the carbon-carbon stretch because there's multiple things that can come in that area. It's not that very diagnostic. What is diagnostic is the proton NMR. So an aryl hydrogen, a hydrogen attached directly to a benzene or a substituted benzene, is going to show up in the region between 6.5 and 8 ppm. It is highly deshielded. Who can raise their hand and tell us why those hydrogens are highly deshielded? This came at the end of last semester. Yes? Okay, so we have the conjugated pi electrons, and those pi electrons are moving. And here's the figure from chapter 14 that shows this really nicely, where we have these circulating pi electrons. And physics tells us that anytime we have charged particles in motion, that creates a magnetic field. And if you know your right-hand rule from physics classes, which I took them way too long ago to remember that, it turns out that the direction of those magnetic field lines in the regions where the aryl hydrogens are, that the magnetic field induced by the circulating pi electrons is going to reinforce the applied magnetic field from the spectrometer. So these hydrogens are feeling an extra strong magnetic field. There's an extra large difference in energy between the two nuclear spin states, and that translates into a high value of chemical shift, which is downfield. Remember, the physicists, we can blame the physicists for the fact that downfield is a higher number in proton NMR. Okay? So that's how we would distinguish protons on benzene rings or aromatic compounds from protons on alkenes. The protons on benzene rings show up in the 6.5 to 8 region because alkenes only have 2 circulating pi electrons as opposed to 6. The magnetic field is smaller, and so the effect is smaller. Notice that benzylic hydrogens are going to be slightly deshielded, but not as deshielded as aryl hydrogens. They're too far away from the ring to feel the impact of the circulating pi electrons. What they feel is the slightly larger electronegativity of the adjacent carbon, and so that slightly deshields them. A regular CH2 group is going to show up at about 1.2 ppm in a normal alkane. Here we see slight deshielding at the benzylic position, analogous to the deshielding you have at the allylic position, another term from last semester that you should remember. So the C13 spectroscopy of aromatic compounds can be quite useful. Who can raise their hand and tell us what is C13 most useful for? What can we determine most readily from C13 spectroscopy? Go ahead. Number of different kinds of carbons, exactly. That's what we typically use C13 as a rapid way of determining the number of different types of carbons. So if we have a monosubstituted benzene, how many different types of carbons do we have? 4, okay? So we would see 4 signals in the C13 spectrum of this monosubstituted benzene. If we had ortho disubstituted benzene, how many different types of carbons do we have in that molecule? 3, okay? So we would see 3 signals. Okay? Let me make sure I draw this right. If we have meta, how many different types of carbons in the meta disubstituted benzene? 4, okay? So we have a plane of symmetry. The plane of symmetry in this case cuts through 2 of the carbons. The 2 carbons that are in the plane of symmetry are not equivalent to each other. So it's 1, 2, and then these are 3, and that's 4, okay? So 4 signals. And if we have a para disubstituted benzene, how many different types of carbons do we have in this molecule? Just 2. We have 2 planes of symmetry in this molecule. And those 2 planes of symmetry mean that both carbons bearing the substituents are equivalent, and each of the 4 carbons that doesn't have a substituent is also is equivalent. Okay. So just 2 here. So simply by taking a C13 spectrum and counting the number of peaks, we can distinguish between ortho, meta, and para disubstitution. Note that this only works if the substituents are identical. If they are not identical, then we have no symmetry, and we have 6 different types of carbons in the molecule. And then we would tell the difference between the monosubstituted and the meta-disubstituted by looking at the proton NMR and determining the integration. We would see 5 aromatic hydrogens in the monosubstituted benzene, and we would see 4 aromatic hydrogens in the meta-substituted by integration. Okay? So counting the carbons in the C13 can tell us the substitution patterns of disubstituted benzene derivatives. Okay? Any questions about spectroscopy of benzenes? I should mention briefly that we won't go into spectroscopy in as much depth as we did in chapters 13 and 14, but whenever we are studying new classes of compounds, we're going to briefly summarize the spectroscopy of those compounds. You will see some spectroscopy problems on your tests. There will be spectroscopy problems on the final exam. And so we've assigned you spectroscopy practice problems. Each of the chapters has spectroscopy practice problems. And so make sure that you get your practice doing that. Dr. Bronson also does a really good job of reinforcing spectroscopy in the 354 lab. So hopefully you're taking that this semester. All right. Let's talk a little bit about interesting benzenes and benzene derivatives. So we can have polycyclic compounds that are aromatic, that have the special stability of benzene. And those are known as polycyclic aromatic hydrocarbons. And here's a common one, benzoapyrene. And as the figure indicates, benzoapyrene is a major component of tobacco smoke. Benzoapyrene can also be found in diesel exhaust, and it can be found in the fumes from charcoal, when you burn charcoal and grill something on charcoal. Benzoapyrene is carcinogenic. Benzoapyrene itself is not actually carcinogenic, but what happens when it's ingested in the body is in order to excrete it, your body will oxidize it to make it more polar so it can be excreted. And in so doing, it makes an epoxide at this position. And that epoxide is very electrophilic and will react with your DNA, damage your DNA, and give you cancer. Okay? So obviously you know that cigarette smoke causes cancer. You may or may not have known that charcoal grilling causes cancer. My grandfather was an organic chemist, and because he knew this, anytime he used charcoal, he would always cover his grill with foil to try to block some of those fumes from getting into his steak. I'm not sure if that was necessary or not. I suppose if you're only grilling occasionally, you should be fine. But if you're grilling things on charcoal on a weekly or more than weekly basis, you might want to cut back a little bit because you could be elevating your cancer risk. Okay? Yes, question. Yeah, so there's a compound called acrylamide, so that's different. So when you fry things, and sometimes they get crispy, kind of like potato chips. They can have acrylamide in it. That's a little different. That's a decomposition product of some of the proteins in those species. So a little different subject, but indeed you can get cancer from certain foods. I wouldn't worry about it a whole lot unless you're eating those foods in huge excess. All right. And then here's some exotic aromatic compounds. We won't spend much time on these other than to mention that they are not planar. This helicene molecule, the way it's drawn funny is because it can't be planar. When you look at the ball and stick model, this has a helical shape, so it's called helicene. This molecule, these hydrogens would be bumping into each other if it was totally planar, so we rotate about these sigma bonds, and that's why it's called Twistiflex. The only reason we show these to you is to indicate that these molecules do not have planes of symmetry. Because they're not planar, there's no plane of symmetry. So they are chiral. You might ask, where are the stereocenters? There are a small class of organic compounds with no stereocenters that are chiral due to having non-superimposable mirror images due to a lack of symmetry. This molecule has what's known as helical chirality. This molecule has what's known as axial chirality. We're not going to say any more about that in this class, other than to just tell you that it exists. And those of you who go on to study organic chemistry at a more advanced level will encounter more compounds in these categories. Okay, so we're just introducing them to you at this point. Okay, so let's talk now more about the special stability that benzene and benzene derivatives exhibit. And we're going to look at heats of hydrogenation. We learned last semester that hydrogenation reactions are exothermic, and we can measure the heat that's given off by hydrogenation, and we can compare heats of hydrogenation to determine relative stabilities. So cyclohexene has a heat of hydrogenation of 28.6 kilocalories per mole. That's how much energy is given off when you reduce this to cyclohexane. Okay. Now, when you reduce 1,3-cyclohexadiene and you obtain cyclohexane, the same product, you get 55.4 kcals per mole of energy released. This is less than 2 times the heat of hydrogenation of cyclohexene. And that's indicative of the stability in 1,3-cyclohexadiene derived from conjugation, the subject of chapter 16. So because the double bonds are conjugated, this value is less than twice that value by approximately 2 kcals per mole. So we say that 1,3-cyclohexadiene has about 2 kcals per mole of resonance energy. Right? Resonance energy was one of the terms we learned in chapter 16. Now, it gets really interesting when we measure the heat of hydrogenation of benzene. It has 3 double bonds. We would expect it to be higher than cyclohexadiene. It is not. It's actually lower than cyclohexadiene. Okay, 49.8 kcals per mole. So less energy is given off when you hydrogenate benzene than when you hydrogenate 1,3-cyclohexadiene. If you multiply this number by 3 and you subtract this number, you get 36 kilocalories per mole. So benzene has 36 kilocalories per mole of resonance energy, a massive number of resonance energy. If the extra stability of benzene was only caused by conjugation, we would expect this number to be about 4 or 5. It should be about twice this number because we have 3 conjugated double bonds instead of 2 conjugated double bonds. But it's way bigger than that. It's more than 30 kcals per mole bigger than we would expect if we're only thinking about conjugation. And so that tells us that there's some sort of extra stability that benzene has. And that extra stability is referred to as aromaticity. In order for a molecule to be aromatic or to have aromaticity, there are 4 conditions that must be met. Okay? The first condition is the molecule must be cyclic. Okay? So, if we have a cyclic molecule, then each p orbital on a carbon is going to overlap with 2 adjacent p orbitals on the neighboring carbons. In contrast, if we have an acyclic molecule, this has 6 carbons just like benzene, but there's 6 carbons in a chain, not in a ring. So this is 1,3,5-hexatriene. This molecule is not aromatic. Okay? It is conjugated, but it's not aromatic because the carbons on the ends of the chain, the p orbitals on those carbons are only overlapping with 1 adjacent p orbital, not 2. So your resonance energy here would be probably about 4 or 5 kcals per mole. Okay? So it must be cyclic. The second point, must be planar. So if we have an 8-membered ring that's cyclic and conjugated, this is called cyclooctatetraene or COT, it turns out that this molecule is not planar. Its conformation is tub-shaped. It bends, okay? So what happens is the carbons on the end will twist up out of the plane, and so this molecule is not planar. We'll talk about why it's not planar in a few moments. And so this molecule is not aromatic. Okay? We'll talk about how you can tell if it's going to be planar or non-planar later on, either at the end of class today or the beginning of class on Wednesday. Okay? Our third point, the molecule must be fully conjugated, meaning that every carbon in the ring must be, or every atom in the ring must be sp2 hybridized. So 1,3-cyclohexadiene is not fully conjugated. It's conjugated, but not fully conjugated because we have sp3 carbons in the ring. So 1,3-cyclohexadiene is also not aromatic. We can tell that by looking at the resonance energy. The resonance energy is way too low for it to be aromatic. Okay. Now our fourth point, this one, we're going to explain the reason for it on Wednesday. It's going to take way too long, so we're not going to explain the reason for it today. We're just going to introduce the rule. Okay. The molecule must have a number of pi electrons that fits the pattern 4n plus 2. All right, now n is an integer. N has no chemical significance, so please do not try to attach any chemical significance to n. It's just an integer. So what it means is that if n is 0, your molecule would have 2 pi electrons. If n is 1, your molecule would have 6 pi electrons. 10 is 2, your molecule would have 10, and so on and so forth, okay? So if a molecule fits into these patterns, then it's going to be aromatic, okay? How many pi electrons in benzene? 6. So benzene fits this pattern. Cyclooctatetraene, how many pi electrons? 8. Doesn't fit this pattern, okay? There's a corollary to this rule. If a molecule fits the first 3 criteria and has 4n pi electrons, then it's going to be incredibly unstable. It's going to be anti-aromatic. So if you had 4, 8, 12, 16 pi electrons, and it was cyclic, planar, and fully conjugated, it would be anti-aromatic and incredibly unstable. Okay, but cyclooctatetraene is not anti-aromatic, it's non-aromatic. Why? Because it's not planar. If a molecule can avoid being planar, then it does, rather than being anti-aromatic, because that makes it incredibly unstable. Anti-aromatic compounds have never been isolated before. Cyclobutadiene has been synthesized before, but it's decomposed. The only way we know it's existed is we've characterized the decomposition products that only could have formed if this had been synthesized, okay? And so anti-aromaticity leads to a high degree of instability, and we'll talk about why that is more on Wednesday. All right, a couple things left. Some other interesting aromatic compounds. Many aromatic compounds are drugs. Here are some very common drugs. And notice that most of them have benzene rings with heteroatom substituents on them to make them polar. That helps them be water soluble, helps them get inside of cells. So these are very common drugs. The last thing we're going to do is get out your eye clickers. Hopefully you brought your eye clickers today. And we've gone over the rules for aromaticity. They're still on the board. You can go ahead and talk to your neighbors and figure out which of the following compounds is not aromatic, okay? Go ahead and talk to your neighbors. Remember, CD is our frequency for the room. Okay, let's try to finish up in the next 15 or 20 seconds here. Get all of our answers in. Okay, any more answers? Going once, going twice. Looks like all we have. Okay, so which one is not aromatic? Yes. Correct. How many pi electrons in number 2? 12, so that doesn't fit the pattern. The others fit the pattern. Here we have 10. Here we have 14. Here we have 6. Okay. One last way to distinguish between aromatic and non-aromatic compounds is proton NMR. Only the aromatic compounds have that specially strong induced magnetic field and the extremely high deshielding. So aromatic compounds will have proton NMR chemical shifts of 6.5 to 8 ppm, whereas non-aromatic compounds such as cyclooctatetraene, because it folds up out of planarity, the hydrogens on cyclooctatetraene will show up in the region for normal alkenes, 4.5 to 6 ppm. So that's another way to tell these compounds apart. Cyclooctatetraene also has alternating bond lengths, alternating single and double bonds, whereas benzene, all the bond lengths are uniform. All right, we'll explain the 4n+2 rule, finish off chapter 17, and start chapter 18 on Wednesday. Please turn in those information sheets if you filled them out. If not, you can bring them on Wednesday.